Welcome to a summary of function transformations. This video will review how the values of a, b, c, and d transform the function of f of x. Let's first talk about the value of a. Y equals a times f of x for a greater than 1 will stretch the graph of f of x vertically by a factor of a. And y equals a times f of x for a between 0 and 1 will compress the graph of f of x vertically by a factor of a. One way to find coordinates of a transformed function in this form would be to find points on the parent function, keep the x coordinates the same, but multiply the y coordinates by a to find the y coordinates of the transformed function. Let's take a look at a graph of this. The red function is the parent function, and the blue function will be the transformed function. So when a is greater than 1, the blue function will be stretched vertically by a factor of a. Also notice that the x-intercepts do not change when we stretch the graph vertically or when a is between 0 and 1 and the blue function is compressed vertically, as we see here. Now let's talk about the value of b. When y equals f of bx and b is greater than 1, this will compress the graph of f of x horizontally. And when y equals f of bx and b is between 0 and 1, this will stretch the graph of f of x horizontally. So again, if we know points on the parent function, we can determine the coordinates of the transformed function with a different value of b by multiplying each x coordinate by 1 over b, or just dividing by b and keeping the y coordinates the same. So we can say the transformed function is stretched or compressed horizontally by a factor of 1 over b. Let's go and take a look at a graph of this as well. So again, the transformed function will be in blue. As b is greater than 1, we'll see that the transformed function is compressed horizontally. Notice that the x-intercepts do change now. And if b is between 0 and 1, the function is stretched horizontally, as we see here. Now before we talk about c and d, we need to back up a little bit and talk about what happens when we change the sign of a and b. Let's first consider when a is equal to negative 1. If y equals negative f of x, this will reflect f of x about the x-axis. Remember, f of x is equal to y, so here we would be changing the sign of the y coordinates and therefore reflecting the graph across the x-axis. If b is less than 1 and specifically equal to negative 1 here, where y equals f of negative x, this reflects the original function f of x about the y-axis because we're changing the sign of the x coordinates or the inputs. Let's take a look at this as well. So we'll decrease a, and as soon as a is negative, it will be reflected across the x-axis. And when a is equal to negative 1, as we see here, the blue function is a perfect reflection of the red function across the x-axis. And we will also have vertical stretches and compressions when a is negative, as we see here. Now let's take a look at what happens when b is equal to negative 1. As soon as b is negative, it will be reflected across the y-axis, and then when b is equal to negative 1, it's a perfect reflection of the original function across the y-axis as we see here. And again, we can have horizontal stretches and compressions as well when a is negative. Now let's take a look at how c affects the graph. If we have y equals f of the quantity x plus c, this will shift f of x left c units. And if we have y equals f of the quantity x minus c, this will shift the function right c units. So if we see x plus c, it'll shift left, and if we see x minus c, it will shift right. This is almost the opposite of what you might think. Let's go back to our graph. Notice when we see x minus a constant, the blue function is shifted right c units. And if we see f of x plus a constant, the graph is shifted left c units. And lastly, we have d. If we have y equals f of x plus d, this will shift the function up d units. And if we have y equals f of x minus d, this will shift the function down d units. And remember, f of x is equal to y, so this is adding and subtracting values to the y coordinates. Let's take a look at this graphically as well. If we have f of x plus d, the function is shifted up d units. And if we have f of x minus d, the function is shifted down d units. Okay, let's see if we can put all these pieces together. For these last two examples, we want to be able to identify the parent function and then describe the transformation. We have y equals negative 2 times the quantity x minus 1 squared plus 3. So hopefully we can recognize this as a quadratic function. So the parent function would be y equals x squared. Next, by looking at the form of the given function, we should be able to recognize that a is equal to negative 2. Since a is negative, this would be a reflection across the x-axis, and there would also be a vertical stretch by a factor of 2. Next, b is equal to 1, so there's no effect on the graph. C would be negative 1. Remember, c shifts the graph left and right. Because it's x minus 1, this would be a shift right 1 unit. And then lastly, d is equal to positive 3. This would produce a shift up of 3 units. We'll stop here on this question. There are 2 other videos that show you how to graph this type of function. In this last question, we have y equals the square root of 1/3 times the quantity x plus 1 and then minus 3. So the parent function would be y equals the square root of x, or the basic square root function. In this example, a is equal to 1, so there's no effect by a. b is equal to 1/3. Remember that b produces a horizontal stretch or compression. Since b is equal to 1/3, this would be a horizontal stretch by a factor of 1 over b, or 1 over 1/3, which is equal to 3. C is equal to positive 1. Therefore, we have a shift left 1 unit. And then lastly, d is equal to negative 3. So we have a shift down 3 units. Okay, that'll do it for this video. Thank you for watching.